Hi everyone, I'm Steve. Thanks for coming along. CMake for the impatient. I suppose I ought to explain a little bit about what I mean by that title. The intention today is not to turn everybody into a CMake expert, just to be clear on that. That would be some trick, given my level of CMake knowledge. What I want to do is try to demonstrate some simple stuff in CMake to try and demystify it a little bit for those that aren't familiar with it. That's because that's where I started with this, as somebody who would look at a CMake file and it would be nonsense to me, didn't understand anything about it. So what I want to do is try to explain my little journey about how I came to understand the basic outline of a CMake file and how that helped me create actual build systems. So, if this works, this is me. You can find me on the internet in various places. This is also me. So for anybody to whom my name is at all familiar, you'll know that I'm a .NET guy, not really a C++ guy, and written a couple of books on .NET, which are completely irrelevant to this talk. So, what about you, then? Is this talk for you? Are you one of these three eggs when it comes to CMake? Perhaps you're a little bit anxious about it, or sarcastic. I know lots of people that are sarcastic about CMake. Bit grumpy, bit nasty. I was probably all three of these a year or so ago when I found that I had to get to grips with CMake in order to make my own life a little bit easier. As I say, I'm mostly a .NET person these days, and the build systems are significantly different for .NET to C++, if you're not familiar. And I started off my career as a C++ programmer, and Microsoft Visual Studio has been a constant companion through several decades of work. But I do remember trying to set up a new C++ project or get to grips with somebody else's C++ project at work and looking at the property pages in Visual Studio and having to check all of these and possibly update them for include paths, where to find libraries to link in, all the various compiler settings, which version of the language to use, although when I first started that was less important because there was only one version of the language. And doing this in a GUI can be a bit of a pain. If you're from a Linux or more Unixy type system background, be more familiar with makefiles, and they have their own challenges. But it is, at least it's in text, right? Visual Studio, not so much. There are property pages that you can export and import that are kind of text, but it's a bit more difficult. And I wanted to find a way of learning CMake in a way that allowed me to set up my own baby project, which was basically for a talk similar to this, rather than mucking around with property pages in Visual Studio. So the plan today really is to show some simple examples. I want to demonstrate that for simple things, CMake is simple. And that may seem counterintuitive. If you've ever seen a CMake configuration for a significant project, then simple is the last word probably on your mind. But I want to introduce some important concepts and hopefully give you a little bit of a clue of how to start understanding a bigger CMake project. Where to begin, some things to look for, some of the important things to look for that will help you identify how a project fits together in big scale as well as in small scale. And hopefully, by the end, you'll be able to recognize the basic structure of a CMake file and by extension, a CMake project, hopefully. And help you get started from scratch if you want to set up your own projects with CMake, which is where I began with this. So there's going to be, this, I hope, is going to be quite a gentle session for a Saturday morning. What I really want to do is try to help, when you see a CMake file, stop you seeing this from becoming gobbledygook, nonsense. This, basically, when I started, I'd look at a CMake file that was, if it was more than just a few lines long, it essentially looked a bit like this. I had no idea what was going on, apart from a few really obvious aspects of it. But it was mostly nonsense to me. So I had to start and try to figure out what I needed to do. I had some tools to help, which I'll come to a little bit later on. But basically, I was seeing this. So here's a simple example. This is canonically, hopefully, the simplest example. I hope you can see that. Essentially, one main file, C++ file, no includes apart from system includes, prints hello CMake to the screen. CMake depends, broadly speaking, on a file called cmakelist.txt. And if you've ever seen a project that has CMake as its build system, you'll be familiar with this. This is the smallest CMake file. This is the hello world equivalent in CMake. To build one file, has no dependencies, and we're going to create an executable called world. The other two lines at the top, the minimum required version is important because CMake has been around for quite a while, has undergone quite a lot of version updates, not all of which are backwards compatible, really. And so you tell CMake what version you're expecting, or what version you've written your CMake file so it knows what to expect. And then we have a project called hello, and really that's just a label that you can hang other things off in your CMake configuration. We don't really care about that in this file, but it has to be there. So for all intents and purposes, that's all you need to know at this point. And what I want to demonstrate is that for simple things, CMake is as simple as this. So I'm going to run a little demo to show you. There are 3 steps to building a project using CMake. One of them is you have to configure CMake itself. The next one is you build it. And step 0 is that you write your CMake list file. But that's basically it. And then the third one on here, obviously, is we're going to run it just to show that it worked. So I have an empty directory in here. So I'm using Windows as my basic platform. I've got my main.cpp, which is exactly as I showed on the screen, and my CMake list file, exactly as I showed on the screen. So the first step is to configure CMake itself. And we use CMake -b and a directory name. And what this command is going to, we're telling CMake to effectively scaffold the build, to create all the files needed to build the project in a directory called bin. And that you can call that what you like. A couple of things to note as I go through. I've not told it that I've got Visual Studio, but it's found it. It's not actually, Visual Studio tools aren't even on my path, but it is installed in a well-known place. So it's automatically detected that I've got Visual Studio 2022 and decided that that was going to be my default tool set. And identify the compiler, goes through and does some other checks. And what that's resulted in is a CMake configuration in my bin folder, which looks a bit like this. So if you're at all familiar with Visual Studio, C++ projects, you'll know what a VCX-proj file is, and that's the configuration for Visual Studio to know how to run a build. Ultimately, it's a tool called msbuild under the hood. And then some other CMake bits and pieces, and there's even a hello.sln, which is the Visual Studio solution file. So we can go in, having run that CMake configuration, we can open that solution file in Visual Studio. I'm not going to do that because it takes forever to open. But that's basically everything there in order to be able to build this into an executable. So we've not built anything yet. All we've done is scaffold the configuration. In order to build it, we run CMake -- build in bin, which is effectively invoked the Visual Studio toolchain to create debug world.exe, which you can see on the command line near the bottom, which I can now run from that. Debug world, which prints hello CMake. So I've created an executable. Applaud now? No. So that's the very basic idea of CMake, is you configure the environment to build, and then you build it from that, and you can rebuild without having to reconfigure every time. A couple of subtleties that, thanks to Leven, pointed out are of I've used, CMake has decided on some default configuration. So just because Visual Studio understands a bit about CMake, it's generated a debug configuration. That's not guaranteed. CMake doesn't guarantee that if you leave out any other command line parameters, you get a debug build. A couple of other things to be aware of, that Visual Studio, by default, creates a multiple configuration solution file. So that VCX proj in the directory listing above contains build configurations for debug, release, and a couple of others that are specified in CMake defaults, but which one you get when you just run CMake -- build is platform dependent and ultimately toolkit dependent. So you can configure this on the CMake command line. I don't want to talk too much about that because I don't understand everything about it. But the basics are that you can tell it to generate a specifically debug configuration so that every time you build it, you get a debug build. And you can tell it to create a separate release configuration.
Sorry, is that actually CMake -- build? Is that the same as make?
So the question is, CMake -- build, is that the same as make? At a high level, yes, it is. So when if you have a make file configuration, and we're going to do that in a minute, when you run make, that actually compiles the code. That's the thing that runs the compilation and produces an executable. So yes, that is the equivalent step to running make. I can change the configuration of the scaffold quite simply on the command line. So CMake understands different generators. So a generator is the thing that produces the configuration. So we've just used a Visual Studio configuration to generate VCX proj files. If I run CMake -big B again in a new folder called GCC, and I use a different generator called Ninja, that's now identified that I've got GNU tools installed. It's actually GCC 14.2. And it's found this actually is in my path, as it happens, the tools to generate a build configuration for GCC. Ninja is slightly different. I'm going to talk a little bit about Ninja in a second. But what we've now got is a new folder called GCC, which I can run CMake -- build GCC. That was much quicker, wasn't it? And it's created me a world.exe that was built with GCC tools. So there we go, runs the same code. Notice in here, we don't have a make file, but we do have a build.ninja. And Ninja is, this caused me to go off into a bit of a rabbit warren of reading documentation, but it's a very, very quick builder. It differs from make in some important ways. So it is a build system like make, but it's independent of the toolchain. So make isn't particularly dependent on your underlying compiler, you tell it what your compiler is. When we ran CMake with Ninja as the generator, that would have picked up what's the default toolkit when I find Ninja, what's its surrounding environment, and it identified GCC, so it generated me a GCC configuration. Ninja replaces Make because Make is a rule-based system that tries to identify all the dependencies within the different targets that you create within the Make file, and then when you run Make, it pulls all those rules together and does the right thing, whatever the right thing for the target. So you can have phony targets for things that don't actually generate an output. You can have ordering within different projects within there. Ninja doesn't do any of that. You have to tell it exactly what to build, and all it does is it goes built or failed to build. But that's the idea. It just does them in order. You give it effectively, with some subtlety, explicitly you tell it what to do. So it's not trying to do anything clever with dependencies or ordering. You have to tell it that explicitly, and the configuration is pretty much by non-humans. A Ninja config is a big block of text, occasionally a big block of binary, depending on the platform, and it's not intended to be directly edited by a human. It's pretty much specifically intended to be created and edited by a tool like CMake. And CMake and Ninja have a very close relationship in that respect, where CMake is good at creating Ninja config. And it's fast. It's really, really quick. Much, much quicker than Make, because you're telling it exactly what to do. It's not going to try and figure anything out when you build the code. Lost my thing. So, headline positives then, hopefully. We've got a common build configuration, our CMake list.txt, from which we can generate build configurations for multiple tools quite easily with some very basic defaults. The CMake lists is completely independent of the tools. You kind of overlay your toolkit via the command line. We used the default, which picked out Visual Studio for me. On a different system, it might have picked GCC or a Green Hills compiler if you've got it, or whatever it is. But we switch on the command line, that -G tells there are some built-in CMake generators that you can find from the CMake help for lots of common toolkits. And I could have chosen the Visual Studio generator explicitly on the command line. But there's a consistent process. That CMake -big B configuration folder, and then CMake --build are basically the two things that you will do probably pretty commonly. And the build process can be version controlled. So Make files have this in a way that Visual Studio configurations don't, because Make files are just text and they are often committed to your code base alongside the code, similar to CMake. So the CMake list.txt, forms part of your code repository, which means that it's CI server friendly, hopefully. As long as you're configured, the configuration of your CI server can be mapped equivalently, so it has the necessary tools installed. It doesn't have to be the same toolkit, but it's pretty common that you'd want to be able to build locally in the same way that your CI server builds, and vice versa. And it's multi-platform, multi-target. So CMake itself is portable, and it has portable targets that you can use for different toolkits, but kind of the build environment can differ between you and your CI server, but also amongst different members of your team. What I'm using it for, or the reason I wanted to get to grips with CMake in the first place for my C++ project is because I wanted to be able to compile quickly the same code for different compilers, because I wanted to check where the pain points were on that. That's a common use case. But even in a workplace, you might have different parts of your team building for different platforms, and CMake gives you the facility to do that. It's not quite as straightforward. If anybody was in Arnie's talk on Thursday about just switch the compiler and all the pain, there are other pain points to using multiple compilers, but CMake takes some of that pain away. So do we need another build system? Make was already mentioned earlier, which has been around for a very long time. And people are familiar with it, despite its foibles. So why don't we just use Make? Make has lots of challenges that have been well known also for a very long time, particularly around multi-file projects and dependencies between them, keeping your Make file up to date, making sure that you've specified the order of projects correctly, etc. And dependency management at compile time and at link time can be a little bit tricksy, particularly in larger projects. But Make does do what Make gives you that just running your compiler tools from the command line. Make dependency management within Make means avoiding unnecessary compilation or recompilation when source files change. But what gives you that extra speed, if you like, is all of the rule-based stuff that Make brings in. Particularly when you have many platforms that you need to build against, or different tool chains that you need to pull in. Various configurations, by which I mean debug versus release, for example. Or the environment, whether you have a fully configured environment that might have a database and message queue and all of those extra bits and pieces that you need to integrate with, or whether you are faking those things out for the purposes of debugging or testing, and so on. So you've got multiple dimensions of configurability within Make. There are also different dialects of Make. Visual Studio tools have long had nmake, which is similar enough to Make file. So an nmake file is similar enough to an ordinary Make file that you look at it and think they're the same, but they're really not. In some really unobvious ways. I mentioned about dependencies and rules and how Make, when you run Make, it's a little rule engine that's going to run to determine what it needs to build in what order, and that can take quite a lot of time. Linux users particularly will be familiar with the idea of auto tools, which the idea of auto tools was to take some of the configuration management away from Make itself, so that when you're building for usually different flavors of Linux, which have slightly different locations for system directories and different versions of the compiler or different warts in the compiler, whatever it is, the auto tools would be platform specific, and it would try to identify what platform you were building for. That added an extra level of configuration against CMake and some extra complexity, not for CMake, for Make, rather. And then other platform differences around things like precompiled headers. So for a long time, precompiled headers were much more difficult if you were using GNU tools because Visual Studio had it built in, but Visual Studio precompiled headers didn't work very well. And then eventually GCC kind of overtook and made it better. But 25 years ago, it was a real problem. So CMake. It does give us cross-platform tooling, predominantly for C++, but it's not C++ specific. But it has become kind of the lingua franca for building C++ projects. It's cross-platform because CMake itself is portable, deliberately so. Available for certainly all of the kind of the major operating system platforms, and some pretty obscure ones too. It has become the de facto standard format for creating a build environment for, again, predominantly C++ projects, but it's not limited to that. CMake is a meta build, kind of in the same way that AutoTools configurations were, where it's sometimes referred to as a makefile maker, although it's a bit more than that. It will generate a make file or a Ninja config, as we saw earlier in kind of a simple example. But its purpose is really, it's not just to make files, it's to make a build environment for your toolkit and kind of customized for your toolkit and optimized for it too. So CMake is very powerful, very, very powerful. With great power comes a huge amount of documentation. If you've ever been to the CMake documentation website, it is vast. And it's extremely comprehensive, but what that means is there's a lot of it. And not all of it is very easily understandable to ordinary humans like me. So what I wanted to get across today is that simple stuff really is simple. Talked a little bit about dependency management and avoiding unnecessary recompilation. So I've got another little demo I want to run. If I can remember how this works. So the idea here is that I've changed my main CPP so that it includes my own header called message.h. And in there, I'm defining a const string that is going to use to print to the screen. And here is my main CPP file in a bare directory. So this time, if I create, I'm going to use Ninja because it's quicker for this, but this works exactly the same way in Visual Studio. So I've created a configuration for those source files, and I'm just going to show the message.h, which I've lined this up wrong simply because the headline was going to change it to that, but we'll change it to something else in a minute. If I run my CMake ---- build and run custom message, it says, hello meeting CPP. If I change the message to something else, I don't need to reconfigure the CMake directory. That configuration stays the same. I just need to rebuild it with ---- build. Which now says hello Berlin. And that's important because what I'm trying to get across here is that running the CMake -big B to scaffold the build, you only really need to do that if you change the CMake lists.txt. Broadly speaking, sometimes you don't even need to do that because of internals of CMake, but as a rule of thumb, if you edit the configuration of the build, i.e. the CMake lists.txt, then you may well need to run the rescaffolding, the -big B. If you change the source files, you only need to rebuild your code. You don't need to rescaffold the build. Scaffolding the build, probably, particularly on larger projects, is the thing that's going to take the most amount of time. So just rebuilding the source files that have changed is going to be quicker. Question.
A stupid question. I don't think you show the CMake lists for this. It must include the main CPP. Do you have to explicitly include the header as well in the CMake?
So you're slightly ahead of me. The question here, I'm not showing the CMake list.txt. In rebuilding the code, I'd only changed the header file. I didn't change the CPP file. The CMake lists, let's just show it here, doesn't mention message.h. It only mentions main.cpp. And that's because there is already built into the configuration this idea that main.cpp includes messages.h, and all of the headline, Visual Studio, GCC, Clang, they have all got facilities to spit out the include dependencies for for all of the CPP files that it's going to use. And CMake makes use of that, as does Ninja, it turns out. So those include dependencies are being brought in implicitly, and you don't need to worry about it. Whether that applies to all toolkits, I don't know. Somebody may be able to enlighten me on that, but certainly on the ones that I've used, that's basically those three, Visual Studio, Clang, and GCC, this works for. So built into the tooling, partly supported by CMake, partly supported by Ninja, in this case, partly supported by the tooling, the underlying toolkit itself, but we've got quite a streamlined build process. Oh, look. Yes, it was time for a demo. That was the demo. So, excuse me. Sometimes you've got dependencies that are not part of your own project. You bring in third-party libraries, or they may be just header file libraries, as in this case. So this is Magic Enum, which is a facility to give you basic string handling between enum values and printable strings. So including, it's a non-standard system include. In my CMake file, I'm telling the configuration where to find the header files to include, so that when I build the project, it looks in this path and adds that because I've put system here, effectively that allows me to use the system include rather than double quote include. There are subtle differences, and that's kind of old history in C++ world. But the headline is that I can easily have third-party includes in lots of different locations, and I just tell CMake in a relatively straightforward fashion where to find them. So we've got the full path specified in here, which is actually relative to wherever I'm running CMake from. Or rather, it's relative to where the CMake lists file that's currently being processed, because they can be nested into a directory tree and include each other. So that's relative to the location of the file that it's in, if that makes sense. Libraries. So some things are not header only in C++, so it turns out. And you might want to have different libraries that you include. So here I'm including the small fast media library for simple GUI stuff. And again, I'm specifying an include directory and the link directories. One thing I didn't mention on the previous slide is the target where I specify in add executable. So that's going to create me something called cards.exe on my Windows box, or just cards on a Linux-based box. I'm telling the target include directory, that's the name of the target that I want to attach these paths to. So when I build cards, it's going to look in those include paths. Your CMake can have multiple targets. You might be creating lots of shared libraries, some static libraries, more than one executable, perhaps a test executable and a main one, and they can all have, well, they would all have to have different names, and they can each have their own set of paths for includes and libraries. So that's one way that you can imagine switching between a debug and release mode build. I'm going to come to that in a little bit more detail. So we've got the full paths for the libraries. The link names are platform agnostic, so to a point. Those are the names defined by SFML for its effectively shared library names with the -d on the end. It turns out that they build effectively the same names for multiple platforms because it's a portable library. Normally, you would expect the names to be the same across different platforms. You may have to watch out for that in your CMake configuration. Not going to go into this in any detail, where the names may differ, and you can choose different names depending on which configuration you're building for. And CMake provides facilities to do that. There's a certain amount of logic handling. Is this a good time for a demo? Maybe it is. Let's talk about debug and release mode. So SFML has pre-built binaries for debug mode and non-debug mode, effectively release mode. And the way that this is handled in CMake is you have a debug configuration and an optimized configuration. Optimized basically means everything that's not debug. You only got the two options there. But that's what it means. This is basically switching between, if you're building a debug mode, and this comes back to telling CMake in its configuration which build type to use. If you're building for a debug target, then it will pick one of the libraries in the top three. And if you're building for any other kind of target, it will pick one of the optimized names. And that is needed here because SFML uses that -d to indicate a debug built dynamic library in this case. And the other ones don't have the -d on. So the names of the files are different. Again, CMake gives us a simple way of distinguishing that within the dependency list for the target link libraries. Slightly better way is that quite a lot of third-party libraries have built-in CMake support. They are what's known as package libraries or CMake package libraries. And we're telling CMake here, with the variable CMake prefix path, where to go and look for a local package. So I've downloaded, probably cloned from a Git repository, all of the SFML repository into that, wherever that libsfml3 is. And I'm telling CMake, this is the root of the tree to go and find its CMake configuration in order to build SFML itself. A couple of other things about static libraries. So SFML defines effectively a definition here for whether you are building for, you want to link static libraries or not. Static libraries are quite big, but it gives you a standalone executable. Shared libraries, you have to worry about whether they're on the path or whether you need to copy them to your output directory. Again, the copying to output directory, CMake provides facilities to do that. Not going to cover that today. And then below that, we've got the CMake invocation find package. Basically find a package called SFML3. And it comes with various different components. In this case, they're called graphics, window, system. SFML has many more. Those are the basic ones if you want to use GUI tools in SFML. So that's not really CMake specific. The CMake bit is we're finding a package given an identifier and a version marker, effectively, and to look for these components within it. And then we're creating an executable called bounce based on a source file given a path. And then the target link libraries, instead of naming the libraries directly as we did here, we're saying we're going to link the component that we named graphics here. Graphics has its own internal dependencies on the other two, window and system, so we don't need to specify those explicitly. Different third-party packages may operate differently. But this should create us a standalone executable. And not in there. In here. So here's this CMake list.txt. Should be exactly the same as what was on the screen. I've already downloaded SFML, hopefully. Otherwise, this is not going to work. I'm telling CMake where to find it and which components to bring in. So if I do, I think for this, I do need a Ninja build, because CMake, I'm not actually compiling SFML here, I'm using the downloaded libraries, and you download a package of CMake, of SFML, according to a pretty specific platform toolkit version of the toolkit. And this is the one for GCC 14. But that's created me, no, I put it in bin, didn't I? A Ninja file to build that project. And I should be able to run CMake --build to create the executable. It's created me an executable in that directory called bounce f, which, if everything's worked, gives me a little GUI. So previous experience with sophisticated third-party packages in C++ from early in my career is that it was a lot more difficult than that. So CMake is taking some of the heavy lifting of attaching your code, or rather attaching a third-party component to your code in a fairly simple way. This idea of pre-packaged components turns out to be really powerful. And a lot of big libraries support this. Not everyone, obviously, but it's worth finding out whether something that you depend on has the facility to support this. Similarly, we can bring in test libraries. So here I'm bringing in Google Test. This is one way of defining that, so get out of the way. Fetch content is something, it does what it says on the tin. It's not built into CMake, it's like a plugin for CMake, but when you install CMake, it comes by default. And we're telling the include fetch content is telling CMake, include this plugin when you run your configuration. And then we're declaring, the fetch content declare tells the CMake configuration where to find I think, probably sources for that dependency. So in this case, we're looking for a library called Google Test, and it's going to come from a zip file that it can find at this URL off GitHub. And then fetch content make available is we're telling CMake to make the library that would be built from that available to the rest of the project defined in this CMake file. So we add executable gtest, and then the target link libraries, gtest main is just a well-known name within Google Test, but this gives me the facility to have Google tests. And I can write a thing. Gtest main means I don't have to write my own main. It's provided for me as part of the library. Rather than depending on the sources from a zip file, I can tell it to depend on a tag in a repository on GitHub, or it might be a local clone. So that would be important. For example, on your CI server, if it doesn't have access to the internet, then you have a local clone of, in this case, catch, that it will go off and get the relevant tag from. But the point here, we've got a library that we're going to call catch2, or that rather is called catch2, that we're going to depend on in our code. And again, we're using catch2 with main so that we don't write our own, but want to write unit tests, there is a simple way to bring in the unit test framework of your choice. I'll put a note how slow to build. I'm not actually going to run the demo for this, but catch2 takes several seconds to build compared to Google Test. It's just an observation. So realistically speaking, we've done some really, really simple things. Real projects in the real world are usually a bit more sophisticated than a single CMake list file and a single one CPP file, perhaps with a single include and a dependency on a library. So you can think about projects having physical versus logical structure. So the physical structure on disk, CMake gives you a way to make that the physical structure, independent of your logical structure. So I can have a flat file that's pulling in source files from lots of different directories. And think of this as all one big CMake lists.txt. So I'm telling CMake include dir on means that including something from dot, wherever the CMake list file is, it adds that to the system include paths, so you can include a file from there. Otherwise, it would fail if it wasn't explicitly on the path. We've got linked directories that there are kind of directives to say that you want to either append a linked directory to the well-known ones that you've already defined, in which case you use after. You can have before as well, so it puts it at the head, so it will find something in there first. But broadly speaking, what we're doing here is pulling together a few of the things we've already talked about, including pulling in some Google test and a load of CPP files for an executable called heating tests. We've also got another target, I think, add executable for the real thing called heating over here, which has got different list of source files, and it's all in one big CMake list.txt, which is probably at the root of your project. And it's not to say that it's wrong to do that. CMake does give you the facility to split things up. So you can, I hesitate to say scatter, but you can put your different CMake list.txt at different levels within your project that you can use to build that local part independently of anything else, and then you can include it from a higher level CMake lists, as we are doing here. Add subdirectory, heating triggers and tests. And what the add subdirectory is doing is looking for a CMake lists.txt file in that directory and effectively including it in the same way that hash include works. So you can modularize your CMake lists. But it's more than just about modularizing it so that they're easy to read. Each of these can be built independently of the others. So these are kind of subdirectory CMake lists, but this is a fully formed CMake list that I can run independently of everything else. So I can just build the tests if I want to, or I can ignore the tests and just build the final output. So that gives you lots of flexibility on how you structure your project, right? And how you break things apart and make them easy to understand. Final word about tooling. How are we doing? I don't know what time is. Am I? Oh, it's not so bad. Thank you. CMake comes with the CMake GUI. I can't recommend it. Unless you already know CMake at a significantly higher level or deeper level than I've gone through today. I genuinely can't make head or tail of it. So, but the two IDE tools that I use commonly are Visual Studio and CLine from JetBrains. So Visual Studio has some rudimentary CMake support. It knows what a CMake lists file is and it will create a project from it. It doesn't give you much help in the way of editing, but it is free with some restrictions. But the community edition of Visual Studio is freely available for non-commercial projects. Similarly, CLine, free for non-commercial use, has much more sophisticated support for CMake. In fact, CMake support is so important in CLine that it's built on it. It's integrated fully into the IDE. So this is where I began. This is the tool. CLine is, I was looking at the output generated by CLine to try and figure out what CMake was doing under the hood. And it gives you all of the visibility, whilst if you don't care so much about that, you can just click buttons in the IDE and it works. And anyway, CLine rocks. I hope I have managed to express some of the endpoints that you can use to identify how if you encounter a project that is built basically using CMake, that you've got some places that you can look to see how the build system fits together. I've seen some systems that are quite big. Even in the world that I usually inhabit with .NET, build systems get big, clunky, and unmanageable, just as easy as they do in C++ land. But, obligatory book remark, that's it from me. Thank you very much. Any questions?
So something I think I've experienced using CMake.
Take two. So something I think I've experienced sometime using CMake is that when making changes to the CMake lists and then regenerating my build system, that there's some changes that seem to propagate when I do that, and others that I need to like clear the CMake cache folder for them to change, and I can't tell which are which, and I feel like I'm just always clearing the cache out of paranoia. Do you have any tips about this?
Or clear the cache if there's any doubt. That's all I have. Yeah.
Okay, so I'm always in doubt, I guess. Thank you.
Sorry, Ross.
I have a question while other people are thinking if they have questions. I had a colleague who was our CMake guy, and he would always insist that we explicitly list all the source files plus all the header files in the CMake file. And I thought that was a bit of a waste, especially the header files. Yeah. Because, but I'm curious as to your opinion. I mean, I don't know if it's a pattern or an anti-pattern to say, take anything that's started at CPP as a source file in a particular directory.
So I have seen documentation and verbal opinion come down on both sides on this one. So for example, CLion, when you use the tooling in CLion to generate your CMake lists, it explicitly lists everything, including all the headers. On the other hand, I agree with you that given that all of the toolkits that I use can automatically identify those dependencies, then it's worse than redundant to immediately list them, because the tool is going to do a much better job of finding out it's easier for you to get wrong if you're explicitly listing it. So I come down on there, let the tool do it, and not explicitly put them. But I hesitate to say, people saying it's best practice. It's not quite as strong as that. But yeah, some people prefer it, some people don't. In the wild, you're bound to see both.
I think there was a certain amount of paranoia that somebody might inject an extra CPP file into your source directory, and totally, like, you'd lose all your money in your bank account.
I mean, it could happen.
One thing about adding the headers to CMake, I believe if you generate an Xcode project, even though like the build system will be able to resolve the header changes, I think like they won't show up in the IDE if they're not in the CMake project. And then
I think it's the same with CLion. I think it's not there. It displays it differently as an independent file. Yeah.
So that can sometimes be like tricky for like trying to just like search for stuff within the IDE.
Yeah.
Hi, I was wondering if you have any tips for migrating to CMake from other build systems.
I guess the honest answer really is no, not because I've not done it. So all I've been doing is making it up as I go along for my own small projects. I would say that CMake is now so prevalent that it's probably worthwhile doing. It's just that I can't help you with how to do it.
Okay, this is fine. Thank you.
I think we're finished. Well done.
Thank you very much. Thanks, everybody.